Hello, hello. So we earlier today we talked about um, this type of equation. We did it with we were talking about specific populations, and we tried to talk about why this was exponential growth. In your homework, you're gonna have a few like this to practice, and then I'm going to talk about the more generic style, which is called separable differential equations. And we'll talk about what all that means shortly. But just a recap. Our job was we have this derivative and it equals some constant times the y value of the equation. And our job is to write an equation that says y equals something and get rid of all of our derivatives. So this is basically saying the rate of change of something is proportional to how much there is. So that's what we talk about. Anyway, step one is I'm going to put it in quotes because it's not really multiplying, but multiply both sides by dx. And when I do that, I'll end up with dy equals 7y dx. So I've gotten the dx over there. I need to get this y over here, so I'm going to divide both sides by y. So we have 1 over y dy equals 7 dx. So I separated separable differential equations. I separated it. Now I'm ready to integrate it. So once my derivative is separated, my y's and dy's are together, and my x's, there are no x's in this case, but my x's and my dx's are all together, I'm ready to integrate. You should hopefully remember that the integral of 1 over y dy is the ln of the absolute value of y. And then we could do plus c, but I'm going to save it and just do it once on the other side. The integral of 7, well, that's a really easy one. At this point, it might be so easy that maybe you forgot, but it's 7x, right? Because the derivative of 7x is 7 plus c. And we're not really done yet. Our job, if possible, our goal is to solve for y. So to get rid of the ln, the inverse of an ln function is e. So we're going to raise both sides to the, or e to this equals e to that. And when we do that, this left side just becomes the absolute value of y. Most of the time it's a positive number, so we can kind of drop it in usual context, like when we're talking about population. I'm worried that I'm not recording. I guess I am recording. Never mind. But most of the time we can drop the absolute values. The left side, this, we can do a little bit of a fancy algebra to it. We can say that this is the same as e to the 7x times e to the c. And we remember, if we have the bases are the same, when we multiply it, we add the exponents. That's what's happening there. And then we should go, oh yeah, e to the c, c is just a constant, e is just a constant, so we can rename this just another arbitrary constant. So we can say e to the 7x times, I don't know, most of the time people use a capital A or something like that. So we end up with something like this for our equation. Let's say, so now we have our differential equation, we've solved it. The question might be, find the particular solution, right? This is an infinite number of solutions because of A. So they might give us something like when x equals 0, y equals 12, right? That could be a particular point that this equation needs to go through. So if we wanted to do that, we could plug in for x and y to back solve for a. And most of the time when they ask you these questions, like the numbers are actually, they work out really nicely. And you'll see that in a moment. So we would have 12, the absolute value of 12, well that's 12 equals, and let me just do it in a different color so you can see what I'm plugging in. 12 equals e to the 7 times 0 times a. Well, 7 times 0 is 0. Anything to the 0 is 1. So really what we just did is we realized that 12 is a. Therefore, the particular solution of this differential equation is the absolute value of y is e to the 7x, well, oops, 12 times e to the 7x. So that's the basic one. I will do a couple more that are maybe a little bit more interesting, but this is the basic one that we solved first, right? And this gets us to exponential growth. Okay, thanks. Bye.